Imagine a world utterly devoid of sunlight, a place where the pressure is so immense, it could crush a submarine like a soda can, and where temperatures swing wildly from near freezing to boiling hot. It sounds like a scene from a science fiction movie, a hostile alien planet. But what if I told you this world exists right here on Earth? And what's more, it's not barren and lifeless. In fact, it's teeming with bizarre and beautiful creatures, forming ecosystems so strange they defy our understanding of life itself. Today, we're taking a deep dive, thousands of meters below the surface, to explore one of our planet's last great frontiers, the hydrothermal vents of the deep ocean. These geological wonders were only discovered in 1977, a shockingly recent find that completely rewrote the textbooks on biology and geology. So strap in, because we're about to journey to a place that will challenge everything you thought you knew about where life can thrive. Our story begins not with a biologist, but with geologists studying the mid-ocean ridge, a massive underwater mountain range that snakes around the globe. They predicted that as tectonic plates pull apart, seawater would seep into the cracks, get heated by magma deep within the Earth's crust, and then shoot back out. They were looking for hot springs, but they found something far more spectacular. They sent down a deep-sea submersible named Alvin, and its cameras captured something unbelievable. Instead of a barren seafloor, they saw towering chimney-like structures, spewing what looked like black smoke into the dark water. These weren't just warm trickles. They were powerful geysers, superheated to over 400 degrees Celsius, or 750 degrees Fahrenheit. The smoke was actually a rich soup of dissolved minerals and chemicals from the Earth's interior, like hydrogen sulfide, iron, and zinc, precipitating as they hit the cold ocean water. They had discovered black smokers. The hydrothermal vents we now know are central to these deep-sea oases. But the real shock came when the submersible's lights illuminated the area around these vents. It was a carnival of life. Ghostly white crabs scuttled across the volcanic rock. Strange, dandelion-like animals were anchored to the seafloor. And most iconic of all, there were dense colonies of giant tube worms, some over 2 meters long, with no mouths, no guts, and bright red plumes swaying gently in the chemical-rich currents. This was a biological paradox. On the surface, nearly all life depends on sunlight through photosynthesis. Plants use sunlight to create energy. Animals eat plants, and other animals eat those animals. But down here, in the eternal midnight of the abyss, where was the energy coming from? What were these creatures eating? The answer is a process called chemosynthesis. It's a revolutionary concept. Instead of sunlight, the primary producers here are bacteria. These aren't just any bacteria. They are extremophiles microbes that thrive in conditions that would be instantly lethal to most other life forms. They have a remarkable ability to metabolize the toxic chemicals gushing from the vents, particularly hydrogen sulfide, the compound that gives rotten eggs their smell. They use the chemical energy stored in these compounds to create organic matter, just like plants use sunlight. They are the foundation of this entire food web. The crabs, the shrimp, the mussels, they all depend on these chemosynthetic bacteria. Let's look closer at those incredible giant tube worms, Riftia pachyptila. Their existence is a masterpiece of symbiotic evolution. That vibrant red plume isn't just for show. It acts like a gill, absorbing both oxygen from the seawater and hydrogen sulfide from the vent fluid. It contains a special kind of hemoglobin that binds to these compounds and transports them safely through the worm's body. Safely, because hydrogen sulfide is highly toxic. But the tube worm doesn't digest anything. Instead, its body cavity is packed with a special organ filled with trillions of chemosynthetic bacteria. The worm is essentially a farmer. It delivers all the raw materials, oxygen and sulfur, directly to its bacterial tenants. In return, the bacteria work their chemical magic, producing all the sugars and nutrients the worm needs to survive and grow. It's a perfect partnership, a self-contained biological factory thriving in total darkness. And they're not alone. The diversity is mind-boggling. There are the Hoff crabs, named for their hairy chests, which are actually covered in bacteria they cultivate and then scrape off to eat. There are scaly-foot snails, a species that incorporates iron sulfides into its shell, effectively building itself a suit of metallic armor. There are blind white shrimp that swarm the vents in such numbers they can look like a living cloud, using heat sensors on their backs to navigate the dangerous temperature gradients. Each vent field, separated by miles of barren seafloor, can be like an isolated island, with its own unique community of species that have evolved in isolation. It's a powerful demonstration of life's tenacity and adaptability, finding a way to flourish in the most unlikely of places. So, these vents are incredible biological hotspots, but their significance doesn't end there. They also play a crucial role in regulating our planet's chemistry. Think of them as the Earth's plumbing system. They cycle elements between the crust and the ocean, influencing the chemical composition of seawater on a global scale. This process has been happening for billions of years, and many scientists now believe that vents like these might have been the very cradle of life on Earth. The chemical-rich, energy-dense environment of early hydrothermal vents could have provided the perfect protected setting for the first complex organic molecules to form, the precursors to life itself. This theory, known as the deep-sea vent hypothesis, suggests that our most ancient ancestors might not have come from a shallow, sunlit pond, but from the dark, hot depths of the ocean. This idea has profound implications, not just for understanding our own origins, but for the search for life elsewhere in the universe. When we look for extraterrestrial life, we often look for planets with liquid water and a comfortable distance from a star. But hydrothermal vents show us that life doesn't necessarily need sunlight. The key ingredients might just be liquid water and a source of geothermal energy. Moons in our own solar system, like Jupiter's Europa and Saturn's Enceladus, are believed to have vast liquid water oceans hidden beneath their icy shells, kept warm by tidal forces from their parent planets. It's highly probable that these hidden oceans also have hydrothermal vents on their seabeds. Could they be hosting their own unique chemosynthetic ecosystems, completely independent of the sun? The discovery of life at Earth's vents has turned these icy moons into some of the most exciting places to search for alien life. Beyond their biological and astrobiological importance, these vents also represent a potential source of two very valuable resources: minerals and energy. As the superheated mineral-laden water erupts from the vents and hits the cold seawater, the dissolved minerals precipitate and accumulate over thousands of years, forming massive sulfide deposits on the seafloor. These deposits are incredibly rich in valuable metals like copper, zinc, silver, and gold, in concentrations far higher than most land-based mines. This has, of course, attracted the attention of mining companies, leading to a new and highly controversial field: deep-sea mining. The prospect is tempting, but the risks are enormous. These ecosystems are incredibly fragile and poorly understood. Mining operations could obliterate entire vent communities, releasing toxic plumes and causing irreparable damage to environments that have taken millennia to develop. The debate over whether we should exploit these resources or preserve these unique habitats as natural wonders is one of the most pressing environmental challenges of our time. And then there's the energy. The sheer thermal power being released by these vents is immense. Scientists have explored the idea of harnessing this geothermal energy. The concept involves placing a device over a vent to capture the hot fluid, using a heat exchanger to boil a secondary fluid, which then drives a turbine to generate electricity. This would provide a constant, clean energy source, right on the seafloor. While the technical challenges of building and maintaining power plants under such extreme pressure and in such a corrosive environment are immense, the potential is undeniable. Imagine a future where remote underwater vehicles and deep-sea research stations could be powered directly by the Earth's own inner heat. It's still in the realm of science fiction for now, but the fundamental principles are sound. From rewriting the rules of biology to giving us clues about the origin of life and the potential for life on other worlds, hydrothermal vents are so much more than just geological curiosities. They are vibrant, dynamic worlds hidden in the deep, a testament to the incredible resilience and creativity of life. They remind us that even after centuries of exploration, our own planet still holds profound secrets and untold wonders. There is still so much to discover in the abyssal unknown. The journey to the bottom of the ocean has revealed a world more strange and more wonderful than we could have ever imagined, proving that even in the deepest, darkest corners of our planet, life finds a way. Thank you so much for joining me on this deep dive into the world of hydrothermal vents. If you found this journey as fascinating as I do, please hit that like button and consider subscribing for more adventures into the mysteries of our world. And I do love to hear your thoughts in the comments below. What part of this hidden world surprised you the most? Thanks for watching, and see you next time.